right, looks like we're live. Hello and welcome to Mr. Linford's live stream. Today is April 15th. The Unit 7 test is officially open for everyone, so I wanted to go through and do a quick review of some of the main topics from Unit 7. It was just a quick unit, just 2 sections, so it really should be a fairly quick assessment for everyone. I'd like to start with Section 11.5. I'm going to review the 2 exit ticket problems, and then I'd like to go over Section 12.2, which is what was assigned today. If you have any questions or if you'd like me to go over anything in particular, please let me know in the live chat to the side. Let me know if there's anything in particular you want me to go over, or if you want me to slow down and re-explain anything. I'm happy to do that, so feel free to let me know. But let's start with Section 11.5. This is the first problem from the exit ticket. And the exit ticket asked us to basically turn this standard form quadratic function into the vertex form. So I'm going to go ahead and do that. I like to leave f of x in the function. Some people like to put it as a 0. Other people like to do everything on one side, but I like to go ahead and work with the f of x. That's just my strategy. So what I'm going to do is complete the square. So I've moved over the constant term, the 2. So it was a negative 2, so I added 2 to both sides. Now what I have to do is work with the b value. So I'm going to, on the side here, take that b value of 2. I'm going to divide it by 2 and square it. So 2 divided by 2 is 1. 1 squared is just 1. So that's the number I'm now going to add to both sides. So we get an f of x plus 3, because these are like terms, so they're going to combine, is equal to x squared plus 2x plus a 1. Now by doing this little side work here, I've forced this polynomial to be able to be factored. So let's go ahead and factor it. We get f of x plus 3 is equal to x plus 1 squared. You can say to yourself, obviously it's a trinomial, so it's going to factor into 2 binomials. And you can say, what multiplies to give you 1 but adds to give you 2? 1 and 1. So hopefully that problem makes sense and you're feeling comfortable with the factoring. So we get x plus 1 squared. And that should happen every time based on picking this value. Now we can go ahead and subtract 3 back over. And we get f of x is equal to x plus 1 squared minus 3. And this is the official vertex form of the quadratic. Remember, these 2 functions are identical. They're exactly the same. If you want, you can just remultiply this and subtract 3, and you get right back to where you started. Okay? No difference between them. The only difference is this form, the vertex form, tells us a lot more information. So let's go ahead and let's identify that information. One of the things that we can tell from this is we know what the vertex is. Now the vertex in vertex form is very easy to find. It's the opposite of this number and this number. So the vertex here is going to be -1 and -3. And then we also need to figure out what are the roots and what direction is this parabola going. So we can say to ourselves, well, let's find the x-intercepts. These are also called roots, by the way. So the x-intercepts are found when the function equals 0. So let's go ahead and let's set x plus 1 squared minus 3 equal to 0. And we're going to solve for x. So I'll add 3 to both sides. And then we can take the square root of 3, the positive and the negative. And then I'll subtract 1 from both sides. So we get -1 plus or minus root 3 is equal to x. Now that's totally fine. This is not going to be a whole number every time. Okay, expect that. It's in most cases it's actually going to involve either fractions or square roots. So that's totally fine. So the x-intercepts here are -1 plus root 3 comma 0. That would be if I listed it as a coordinate point. This is one of the x values. The other x value would be -1 minus root 3, comma 0. Okay? Remember, x-intercepts are coordinate points. They're where you cross the x-axis. They're where y, or the height, f of x, the output, is 0. So we have our vertex. We have the x-intercepts. And maybe the last thing to do is talk about the concavity. Now, the concavity is the direction of the parabola. Are we opening upwards or are we opening downwards? Well, the easy way of deciding this, let me see how many viewers we got. 2 people. Okay, so of my viewers, I'm going to give you a minute to see if anyone can type this to the side here. What is the way that we determine the concavity of this quadratic? If we're talking about the graph of this quadratic, it's a parabola. How do we know if it's opening upwards or if it's opening downwards? Is it concave up or is it concave down? How do we know based off of this vertex form? So I'll give you a minute to think about that and try to type a message. I know there's about a 30 to 45 second delay. But while you're doing that, another way that we can figure out the concavity is by simply graphing the vertex and graphing the x-intercepts. By putting together a little graph with these 3 points, we can obviously quickly tell, is it opening upwards or is it opening downwards? But it's sometimes nice to be able to just look at the function and to tell right away, I know that's an upwards opening parabola or that's a downwards opening parabola. Concave up or concave down. Now I'm going to give you guys, I'll take one more minute to see if anyone can type in the live chat what's going on here. How do we know if we're concave up or if we're concave down for this parabola? While you're doing that, I'm going to pull a Mr. Tuttle. I got a thermos of coffee here, actually. I'm going to, one sec. All right. I literally poured myself a thermos of coffee just because I needed it this morning. I'm still working on it, and I'm like, oh my gosh, how does Tuttle drink all of this? And then I thought to myself, wait a minute, the amount of cups of coffee I make a day probably equate to that. All right, not seeing any comments over in the live chat, so let's go ahead and let's answer how we decide whether or not the parabola is concave up or if it's concave down. Well, if you remember when we were manipulating the functions, the value that we multiplied the squared component by, so whatever, and I'm going to try to, I'll erase this and try to fit it in over here, whatever number was multiplied by the either x squared or whatever the whole quantity squared was, controlled how wide or how thin the graph was. It also controlled if it was up or down. So what number is out front of the parentheses here? That's just a 1, right? There's like an imaginary 1 out front. That's a positive 1, okay? You don't see a negative sign anywhere there, do you? You don't see like a negative 1 or anything. No. Instead, we just have a positive 1. That number being positive means our graph is opening upwards. So we are concave up. So it's parabola opening upwards. It's going off towards the infinities, or going off towards the positive infinities, both ends of it. This is going to help us, this number here, not only decide how wide or how narrow the graph is, but it's also going to tell us if we're opening up or down. So positive opens upwards, negative opens downwards. So if you have a positive x squared or a positive, whole unit, or if the whole squared quantity is positive, then we're good. If it's negative, we're opening downwards. So this number right here is the thing that determines that. Now let's go ahead and let's take a look at problem 2 from the exit ticket. This one asked us again to put it in vertex form. So I'm going to do that. If you remember, when we complete the square, we cannot have the leading term be anything other than 1. So to force it to be 1, we said simple fix. Just divide both sides by the leading term. So I've divided both sides by 3. I'm going to get f of x divided by 3 equals x squared minus 4x plus 13 over 3. Now I'm going to subtract the whole number from both sides. Well, not the whole number, but the constant number from both sides. The 13 over 3 is going to be subtracted. So I have f of x over 3 minus 13 over 3 is equal to x squared minus 4x. So this is just like normal. You don't always have to have whole numbers when you're completing the square. Obviously, quite a lot of the time, you're going to end up with fractions, and that's okay. Notice that I'm still working with the f of x, and I'm keeping this term here, f of x divided by 3. If you didn't use the f of x, like if you used a 0 in its place, you would end up saying that just cancels out to be 0. But we're going to remember, we're going to want that 3 back in the end. So I'll just leave it there as is. Now I'm going to take this middle term, negative 4, and I'm going to divide it by 2, and I'm going to square it. So negative 4 divided by 2 is negative 2, and when I square that, I get a positive 4. So this little work here tells us what we have to add to both sides. Okay, so on the left-hand side, we're going to have f of x over 3 oh boy, well, let's see. Negative 13 over 3 plus 4. Well, if I wanted a common denominator, I'm going to multiply the top and the bottom by 3. So what's that? 12 over 3. And negative 13 thirds plus 12 thirds is negative 1/3? Yeah, that should be right. I like when mental math works out nicely. So we have negative 1/3 equaling x squared minus 4x plus 4. Now, the right-hand side must be able to be factored, and in fact it does. It factors down to an x minus 2 squared. I can then take f of x over 3. Let me write this a little neater here. We're going to take f of x over 3. I'm going to add the 1/3 to both sides, so we get x minus 2 squared plus 1/3. And then let's multiply both sides by 3. So we get f of x is equal to 3 times x minus 2 squared plus 1. Please make sure you don't actually distribute into the parentheses here. Some students were asking me, why can't we distribute into? Well, remember, there's an exponent on the outside here, right? So you can't distribute when there's an exponent on the outside. You'd have to apply the exponent first, which means you would actually have to multiply x minus 2 and x minus 2. That would just get us back to where we started, okay? So don't worry about that. Don't actually distribute in, remember. Oops, sorry about that. Sorry, Dad. All right, let's get back to this problem here. We've just converted it to vertex form. Great. And now everything wants to break. Let's see here. Let's see if I can get my iPad back to connect. And all right, we should be good now. All right, now we have the quadratic written in vertex form. So we've taken it from standard, put it into vertex form, and you'll notice that this last step I did here where I multiplied both sides by 3, that wouldn't have happened if that was a 0. So if you put it into the form where you just worked, if you set it equal to 0, that really wouldn't have worked in this case. So sometimes it's nice to be comfortable working with this f of x over 3 business. It's just kind of a nice way of remembering, hey, at the very end, you got to remultiply everything by 3. So let's remind ourselves of a couple key components here. We need to know the vertex. Well, let's see. The vertex here is going to be positive 2 and positive 1. Remember, we take the opposite of this value. That was a negative 2, so we have a positive 2, and then we have a positive 1. And we also need to find the x-intercepts, and we need to tell the concavity. Now, let's start with the concavity. Is this parabola opening upwards or is it opening downwards? Well, remember that we talked about what is the number that's being multiplied by the squared quantity. Here is the squared quantity. So what number is multiplying to it? What's that scale factor? It's a 3. Is it a positive 3 or negative 3? It's a positive 3. So that means we are opening upwards. Since this number here is positive, we're opening upwards. By the way, this number that we're going to have down here is the same thing as the leading coefficient. So you might say, if the leading coefficient is a positive number, you're going to open upwards. If it's a negative number, you're opening downwards. So try to picture what's going on here. We have a vertex of 2, 1. So we're in the first quadrant, and we're opening upwards. Do you need to solve for the x-intercepts? No, you actually don't, because if you picture what's going on, you're over here, and you're opening upwards. Will you ever cross the x-axis? No. In fact, there are no real x-intercepts here. You could set this equal to 0 and solve it. You could go back to the original problem and do the quadratic formula if you wanted to. But what you would find is the x-intercepts that you get, those values, are actually complex numbers. They deal with I. So there's no real numbers here, and that's okay. That can happen. If your parabola's shifted up above the axis or below the axis and it's going downwards, it's just not going to cross the axis. And that's fine. That happens quite a lot, actually. So in this case, by knowing the concavity and knowing the vertex, we really didn't need to solve for the x-intercepts. So we were able to save ourselves some time there. Now what I'd like us to do is I want us to go and take a look at some of the work that we're doing today, section 12.2. In section 12.2, you should be looking at different exponential functions. So here we have various exponential functions. That's where we have a number raised to an exponent. This is different than a quadratic. So let me take a little time here to remind ourselves. A quadratic was f of x equaling a variable squared. An exponential is a function where you have some number, whether it be 2 or 7 or 5 or a fourth or whatever, I'll call it b, to the x value. In a quadratic, the number that was squared was the variable. In an exponential, the variable is the exponent. So that's the difference here. And that's why their graphs are going to be different. One had a parabola, where it was the same on both sides. It was symmetric. The other, yeah, it's going to have a curve either upwards or downwards, but it's only going to be on one of the sides. So what we need to do here, when we look at a function like this, we want to know, is this parabola an exponential growth or an exponential decay? Meaning, does its graph increase as x increases, or does it decrease as x decreases? So let's take a look here. Because this number is a 7, because b here is 7, I know that this is exponential growth. We're going to be increasing because we said in our video, if this number, if this b is greater than 1, you're going to be increasing. You're going to have exponential growth. Similarly, if we take a look at the problem here, this is, by the way, problem 2 from the independent practice, and that's problem 3 from the independent practice. If we look at where b here is 1/4, we're going to have what's called exponential decay. And this occurs because b here is between 1 and 0. If b is between 1 and 0, then it's going to be an exponential decay. It's going to be decreasing over time. Now, what are some other key components that we need to know here? Well, we know that the domain is always going to be negative infinity to infinity, and the range is pretty much always 0 to infinity. We know that there are asymptotes at the x-axis, but let's identify some key points here. I'd like us to identify some key points because that helps us when we actually need to go and graph what's going on. So let's start in the first one here. What happens when x is 0? Well, if you plug 0 in for x, 7 to the 0 power is just 1. So that's a key y-intercept. And that's going to be the same thing down here. When you plug 0 in, what's 1/4 to the 0 power? 1. So that's the y-intercept every time. Now let's take a look at the unique key points that they each have. Let's plug 1 in for x. When you plug in 1 for x, you would get a 7. And when you plug in 1 for x here, you would get a 4th. You get the identity. You get the exact value, okay? Whenever you plug 1 in, you get that value. Anything to the first power is just itself. Now, it might also be helpful to go in the opposite direction. Let's plug in -1. What would 7 to the -1 be? Well, remember, that's 1/7 to the +1. That's when we had to actually flip the value around. So -1 would give us 1/7. What about over here? What would -1 give us for 1/4? Well, 1/4 to the -1 power is the same as 1/1/4 to the +1. And if I flip and multiply, I would just get 4. Hey, that's actually pretty helpful when we need to graph this. -1 here would get us a 4. Knowing these 3 points, I can pretty accurately sketch a little graph of what's going on here. And in fact, we can take a look at the graph in Desmos. Let's see here. I'm going to go into Desmos and I'm going to type in f of x, so f parentheses x, equaling 7, and then I'm going to hit the exponent button here, and I'm going to put the variable as x. So here is the graph that we get. Notice it is an exponential growth, and if I wanted to, I can click on the graph itself, and I can see here, if I'm touching the graph, the y-intercept is 0, 1, and let's scroll up, and let's see what happens when x is 1. When x is a 1, and you got to be careful here so you don't overshoot it. Just did. There we go. It's a 7. Do you see that? Right there. When x is a 1, y is a 7. Close enough. You saw it. All right. Now, the other one we said is when you're at -1, you should be 1/7. Now, 1/7 as a decimal is about 0.143. So I'm on the graph. I'm trying to get to -1 here. And let's see. It's right about -143. Let me see if I can zoom in a little. Maybe that'll help. But really, we should be seeing exactly what we calculated. There we go. -1 and 0.143. So we get the exact points that we were talking about here. Now let's change it. Instead of having 7 to the x, we can have 1/4 to the x power. Here we'll notice that what's changed, it's now become an exponential decay problem, and we still have the intercept 0, 1. When x is a 1, you see we get 0.25. Hang on a sec. Let's see if I can get it. Why do they make this so difficult? All right. When it's a 1, we get 0.25. Come on. Oh, geez. Whatever. You can pause the video. There we go. So when it's a 1, we get a quarter, which is exactly what we expected. And we also said when it's -1, we should have a 4. So let's see if we have that here. When it's -1, we have... Oh, come on. 4. Just missed it. Whatever. You can see that when it's -1, we end up with 4. So these are the values that we expected to have, and in fact we do. If we plotted them, we could probably accurately get a little sketch here. Remember that in both of these graphs, the asymptote is the x-axis. Our graph, this red line, gets incredibly close to the x-axis, but it never actually touches it. You can in fact zoom in, and you would see... Oh boy, we gotta way zoom in, but here we go. Now you can start seeing, oh, look right here. We're incredibly close, but we're not actually hitting the axis. So let's go back to our practice problems here. And let's take a look at a couple more examples. These were from the independent practice, and I wanted people to take a look at these negative examples with negative exponents. So we have 5 and 6 from the independent practice. Some people thought, well, you didn't tell us what to do with negative exponents. And I thought, didn't we work on that before? Let's take a look here. 1/2 to the negative x. That would be the same as 1 over 1/2 to the positive x, right? Which would be, if I flip and I multiply, 2 to the x power. I'll go ahead and show a little more of the work here. When it's 1/2 to the negative x, remember that's negative x over negative x. Well, 1 to the negative x power means move down to the denominator, and 2 to the negative x power means move up to the numerator. What's 1 to any power? It's just 1, right? So 2 to the x. There we go. So that's another way of thinking about this. So really, this is the function that we're working with here. So this is the same thing as 2 to the x. And then down here, if I had 2 to the negative x, that means I got to have 1 over 2 to the x power, which is the same as 1/2 to the x, because 1 to any power is just 1. So really, 2 to the negative x is 1/2 to the x. This was just a little practice I wanted you to try doing with negative exponents, just to remind yourself of how they move around the fraction line. Okay, now that we have 2 to the x, we know that it is going to be growth, an exponential growth problem. It will have the y-intercept of 0, 1, and it'll have the special points. If I plug 1 in, we'll get 2, and if I plug in -1, we'll get 1/2. If I look at this example of 1/2 to the x power, I know that this is going to show exponential decay. It's going to have the y-intercept 0, 1, and when I plug 1 in it, it'll have 1/2. But when I plug in -1, 1/2 to the -1 power, it'll give me a 2. So let's take a look back in Desmos here. We want 2 to the x power and 1/2 to the x power. I'll try to do that in 2 examples here. So here's 1/2 to the x power, and then let me do another one here. F of x equaling 2 to the x power. Okay, 2 to the x power is in blue, 1/2 to the x power is in red. So you can see 2 to the x power here is in fact an exponential growth problem, while 1/2 to the x is an exponential decay. It's decreasing as x increases, while the blue one is increasing as x increases. They both should have the y-intercept of 0, 1. The blue graph does, and so does the red graph, 0, 1. Now, we wanted to make sure that they had those special points to them. So we said for the blue graph, when you plug in 1, you should get 2. So let's plug 1 in here. Let me zoom in a little bit. When x is 1, we should have a 2. Oh, did you see it? Hold on a sec. Let me see if I can get there. There we go. 1 and 2. And when it was -1, we said we should expect a half. Almost. There we go. -1 and 0.5. There we are. So we have the exact points that we expected for this. Now let's go ahead and switch over to the red graph. And let's see what we have here. We expected when x was 1 to get a half. So x is 1 here. And did you see that? It was 0.5. Let's almost, there we go. When x is 1, we have 0.5. When x is -1, we expected it to be 2. So -1 and 2. There we go. So we get the exact points that we expect here. We can see what the graph looks like. But if we needed to, we have those 3 points. We can kind of sketch what it would be. Now, keep in mind, one thing I want to point out to you, how rapidly exponential problems grow. Take a look here at this curve. Look at how quickly it's jumping upwards. From 0 to 1, it only went up 2 units. From 0 to 5, it's gone up. Let's see where we're at here. When it's 5, we get, come on, 32. It's jumped up basically 30 units, or I'm sorry, 32 units. And then look, before we even get to 10, look how high up we still go. X isn't even at 10 yet. Let me try to get on the graph here. X here is in 7, and we're at 107. Look how fast this is going. Oh my gosh, when will I even hit 10? I'm in the 500s now. I'm in the 600s, and X is still at 9.2. So the idea here that I want you to see is how quickly exponential growth occurs. This is what's called the doubling effect, because this is 2 to the x power. Every time you're doubling, you're doubling, you're doubling again and again and again. That is incredibly rapid growth. Is it different than quadratic growth? Let's take a look here, and let's look at the differences between the exponential in blue, and I'm going to put in the quadratic function, the parent function for the quadratic. So x squared. Let's take a look here. I'm going to zoom in a little bit. The quadratic is in green, and the exponential is in blue. So, okay, there's a little difference here down at the bottom. And then right about here, it looks like, oh, that green graph is actually higher than the blue graph. It looks like quadratic growth is actually more rapid than exponential. But wait a minute. Look what happens up here. Right at this point. At 4:16, when x is 4, they start to separate. The blue graph, the exponential, is now on top of the green. This one is increasing much faster. And as we zoom out, we can see, oh yes, that blue graph is on the inside here. It keeps increasing much, much quicker than the quadratic. So what will eventually get you larger and larger values quicker and quicker? 2 to the x would, not the x squared. So that's the power with exponents. It sometimes takes a little slow. It's a little slow to start, takes a little bit, but over time, it will very quickly, very rapidly start increasing, okay? That's all that I had for us to review today. Hopefully this is making sense to you. You're feeling comfortable with it. I don't really see any comments over in the live chat, so if you do have any questions or comments, feel free to let me know. My email is let's see here. Get my stylus to connect. My email is klinford, that's KLINFORD, @wccnet.edu. Let me know if you have any questions or comments or want to go over anything more. And until next time, take care.